or Smart Star, probably to call it. This is joint work of two groups or institutes at the University of Stuttgart, that's Bernhard Mitschang's and Leymann's institutes. And Pascal Hirmer from Bernhard Mitschang's group will present. The floor is yours.
Thank you very much for the introduction. Can everyone hear me properly?
No.
No? Okay.
Good guys.
Perfect. And no feedback whatsoever? Okay, so we can start. As Mr. Deskov already said, it's a joint project called SitUp, and the paper I'm going to present is called SitRS, a situation recognition service based on modeling and executing situation templates. SitUp is funded by the DFG, which is the German Research Foundation. Okay, as you can see, the co-authors on my paper were Matthias, Wieland, Holger, Schwarz, Bernhard, Mitschang, Breitenbücher, and Leymann. Let's start with an introduction of the topic. As you all know, today there's an increased interconnection of IT systems and physical objects. So you all know about smartwatches, you all know about smartphones, smart production systems, smart home technology, and so on. In the context of this presentation, I'm going to call these objects smart objects. So when I'm talking about smart object, I'm talking about one of these things. As you may also know from the previous talks today, these smart objects produce a huge amount of sensor data by a huge amount of sensors. So to properly use these objects, we need a uniform sensor data integration and sensor data processing, which basically enables the Internet of Things. Okay. The main focus of our work is situation recognition. So I want to start with a definition of a situation. We defined a situation as an occurring event in a smart environment, which is, for example, a smart factory, a smart home, and so on. So we could also define a situation as a change of state in such environments. I got some examples here. For example, a production machine is damaged, a server load is critical, a room is occupied, or a room temperature is increased. So we're talking about change of states. These situations are always recognized based on a large amount of sensor data. However, these raw sensor data, which are very low level, are difficult to process. So as a consequence, we need a means to extract high-level situations based on raw sensor data. And this is our contribution in this paper. Okay, let's have a short look at the paper contribution and the agenda. So what we were developing a concept and an architecture for a situation recognition service, which is called SitRS. It's a cloud-based service which enables firstly automated sensor binding and secondly the processing of raw sensor data to recognize the situations I defined on the previous slide. Let's have a short look at the agenda. I will first talk about situation modeling using a model we invented called situation templates. After that, I will introduce a method to recognize situations and the resulting situation model. I will talk a bit about the SitRS architecture, and finally I will give a summary and an outlook of the concepts. Okay, I want to start with some basic concepts which are necessary to understand the whole approach. Imagine you got a smart environment, which could be a smart home, for example, and in this smart environment you got a smart object. So to enable everyone to understand this example, I want to take a smart web object that everyone knows, which is, for example, a computer, which contains a lot of sensors, a CPU sensor, a CPU load sensor, available RAM, and so on. So this object produces a lot of sensor data, which are pushed to this data level. So in this level are contained all the sensor data produced by the observable objects. However, those are low-level data. For example, if we monitor the available RAM of a PC from the sensor just tells us you got 1000 MB. However, what am I doing with this value? So what we need is context. So we need another level above that to enhance this raw sensor data with information to generate context. So basically what we could do in this example, the context would be the total RAM is, I don't know, 12,000 megabytes. So we know, is our RAM full or is it empty? We can use this context to derive high-level situations. So a situation for a computer or a server could, for example, be the computer is ready if the RAM isn't full, or it is critical if the RAM is full. So that would be a typical situation in this use case. On top of that, you can now build situation-aware applications that can register on the situation recognition and can adapt to the situations that are recognized. In this use case, if the RAM is full, we need to react. We need to decrease the memory, for example, that is consumed. Okay, so much for the basic concepts. To define situations, we invented a model called the situation templates. As you can see, this is also derived from this model. On the bottom level, we got context nodes, which are basically representing the sensors that are contained in a smart object. For example, for our use case, where we monitor a server, we got a sensor that produces output for the CPU load, the free memory, and has some kind of heartbeat, a status monitor. These raw sensor data can then be compared with fixed values using so-called conditions. The output of the condition is, of course, a Boolean value and can be concatenated using logical operations like AND, OR, XOR, and so on. The result of this tree is the situation with, in this case, is the critical state. So, to summarize, the state critical is reached if the CPU load is larger than 90%, if the free memory is lower than 100 MB, and if the status monitor doesn't set a heartbeat. Okay. To recognize these situations based on situation templates, we define a method. And this method contains of 3 simple steps. In the first steps, we of course have to register our sensors. This is usually done by a technical expert who knows about the sensors. He knows about the sensor quality, about the data type that is produced, about the sensor frequency, and so on. After the sensors are registered, you can model situation templates based on the registered sensors. These situation templates are then used for situation recognition. So they are transformed in an executable representation, which is executed, and the output of this execution is the situation. So let's have a more detailed look at the third step, the situation recognition. First of all, you can register for a situation. To do so, you need a situation template and the object to be monitored. After that, the situation template is transformed into an executable description and can be deployed in an execution engine and can finally be executed in this engine. The result of the execution is, as I said before, the situation. And as you can see here, the execution of the situation template is repeated n times until the situation is deregistered from SitRS. So the user can decide how long he wants to recognize the situation for a smart object. Okay. The output of the recognition is a situation object. Here's an example for a situation object. We can have a more detailed look at it. It has several properties. The situation that is produced has a name, an icon, which aren't that important, information about the observed object, the location, the timestamp when it was detected, which is very important if you want to process the situation. You want to know when did the situation occur, a description, the situation template that has been used, and also the recognition system that was used, which is pretty interesting because our approach enables a lot of different systems to recognize situations based on transformed situation templates. So in this example we use Node-RED, which is a flow-based execution engine for the Internet of Things. Maybe some of you have heard about it. Which is also important is the quality of the situation. As you can see, this situation has a quality of 95%. The quality depends on the quality of the sensor values, of course. So if the sensor values that are produced aren't correct, then the quality of the situation is also not that correct. So you can compute the quality based on the sensor data that is being produced. Okay, so now let's have a look at our architecture. You may recognize the different levels from the slides before and also from the situation detection pyramid. On the bottom we got physical objects, which are smart objects basically containing a lot of sensors. Now I can tell you how to apply the method based on this architecture. So first of all, you have to register your sensors. This is done by the technical expert, as I already said. If a sensor is registered, you can connect to the sensor using sensor adapters and provision the sensor data using a uniform resource, which in our case is a REST resource. So we take the data from the sensors and we provision the sensor data in a service-oriented way. Next, after the sensors are registered, you can either model a situation template or you can choose a situation template from a repository. So the chances are always high that someone has already modeled a situation template, of course. After that, you can use the situation registration service and register on the situation. By doing so, the situation template is mapped onto an executable description, is executed in the situation recognition system. But during the execution, it is of course accessing the REST resources to get the sensor data from the smart objects. The result is the situation object I introduced on the previous slide. Okay. I want to talk about the use case for all of this. Maybe you're wondering, how can I use these situations that I've computed? What we're doing in SitOpt is we enable situational control flow modeling. So imagine there are analysts and planners which can model their process as a standard workflow. And what domain experts can do now, they can model their knowledge as situation template. For example, whenever event 5 happens, always situation X occurs. Together, situational exceptions can be modeled. You can annotate the situation to a standard workflow, and you can handle different situations with situational workflows. I want to show an example for this. Let's have a look at this workflow. It is annotated with a situation which is recognized by the SitRS approach. For example, in these steps, SitRS, if SitRS produces a situation in these two steps, for example, machine failure or material missing, you can react and you can execute another workflow fragment for that. Okay. Now I want to show you our prototypical implementation of SitRS. You might recognize this architecture. It's basically the same with some minor differences. I just want to talk about the technologies we used because there are some interesting stuff that we used. I won't be focusing on the databases because they are still work in progress and they are not that important for the approach. What is very interesting is the resource management platform in the middle. As I already said, we are connecting to the sensors and we are provisioning the sensor data in a service-oriented environment. So we provision them to the internet basically. What we are using is OSLC, so OSLC is a specification to integrate lifecycle tools. We just use the idea of OSLC. So we got nothing to do with the lifecycle tool integration. We use the idea to provision data as a uniform REST resource. OSLC provides some concepts to connect to data sources and to provision them. So our basic concepts are based on OSLC. As you can see in this picture, we got this data cache in the resource management platform. And you might wonder why we're doing this, because everyone who knows about IoT would expect a push approach. And what we are doing, we don't do just a push approach to the situation recognition. We got this data cache in the middle, which is accessed by a pull of the service that provides the resource. Why are we doing this? We are doing this because we need sensor data all the time. So if we want to recognize a situation at a certain time, we need to have access to sensor data. And if the sensor doesn't produce any data in this moment, we got a problem. So we compute our situations for a certain time, at a certain time. And that's why we need the data cache. However, there are also some problems with that, of course, because sensor data are never new if they are stored in the data cache. So this leads, of course, to a decreasing quality of a situation. The older the sensor value is, the less the quality of the situation. So it could be that the sensor down here produces a sensor value every 2 months and stores it in the data cache. If we access the data cache, we also store a timestamp, of course. And using this timestamp, we are computing the quality of the situation. Okay, maybe I could take some words for the other technologies we use. The mapping isn't that interesting. It's Java, JAX-B, and JSON. JAX-B because our initial situation template model is based on XML and we want to work with Java objects. The execution is, as I already mentioned, in Node-RED, which is a product by IBM, I guess. It's a flow-based engine for the Internet of Things, which is always executing nodes in a flow-based manner. Okay. So what we did, we measured our approach, and in the area of situation recognition, there are a lot of other approaches. There are approaches that recognize situation based on ontologies. Some people use machine learning for this, and we compared their approaches with our approach. And in some of the related work, they said that taking some seconds or even up to 30 seconds is okay to compute a situation. However, there are also critical environments, such as smart factories, where it's important that you create the situation, for example, for machine fares, or if there's some kind of alert, I want to have the situation now and not in 30 seconds and not in 1 minute or half an hour. So for us, the efficiency of the approach is very important. We got some very interesting good results. It's not that readable down here, so I put the data for one situation to be recognized in this table. We measured the transformation of the situation template to the executable model. We measured the deployment in the execution engine, and of course, the most interesting part, which is the most time-critical part, we measured the situation template execution. And as you can see, we got very good results. We could recognize the situation in 5.6 milliseconds. What I forgot is I wanted to show you the use case, of course, that we've measured. And it was this use case. What we did is we got our SitRS service on our private cloud environment, which is a pure flex with an OpenStack. And we monitored a computer, which was in this case my computer, which contains these sensors, and we used exactly this situation template. So of course this is a very simple example. However, situation templates won't be a lot bigger than that, in my opinion. Okay, so as you can see, of course the measure time increases with the more situations you recognize. Which is pretty interesting is that we measured in Node-RED parallel runtime, so the recognition of many situations in parallel against sequential execution. And as you can see, for the sequential execution, the results are as expected. So the results are 57 milliseconds, which is as expected because for one situation we took up to 5.6. So, however, in the parallel execution, we took up to 404, which is a lot more than we expected. And what we did is we had a deeper look into Node-RED, and we saw that there is no real parallelization in Node-RED. It's still sequentially, and there are some huge schedule issues. So these measurements could be explained by that. So what we will do in the future is we will use some other execution engines to recognize situations. For example, we are currently working on complex event processing approaches to cope with these issues. Okay, to summarize, SitRS is a general purpose situation recognition service that can be used for different use cases. What we did was we defined situation templates to model situations which are based on this situation detection triangle, which I called pyramid earlier. I meant to change that, sorry. We defined a situation model, which is basically for defining situation objects that are characterizing the state of the environment. So if a state has changed, a situation occurred, we got a new state in the environment, and we got the situation objects that is describing this state. Also, through our abstraction from situation templates to the executable model, we enabled the integration of different processing technologies. All you have to do is you have to change the mapping from the currently XML-based format to the executable model. One could use data streaming engines, complex event processing as we are currently working on, and other Internet of Things technologies. Our initial goal was to recognize situations based on raw sensor data, which could be achieved with this approach. In the future, we will work on integrating other event and data stream processing technology, which we are currently doing. We are working on an ontology-based sensor registration and integration to enable a semi-automatic sensor registration, which is currently done manually. So if you want to register your sensors, you need this technical experts, and he has to fill in all the details. And furthermore, we want to enable automatic situation recognition based on historic data. As I mentioned, currently we can only take current data that was recently produced by the sensors. So we are not looking at any histories. And also we want to kind of formalize the approach. So we want to create a model that formalizes situations. What's the situation? What's the situation object, and so on. Okay, how much time do I have left?
5 minutes.
Still 5 minutes left?
Yes.
So I could take the time for the backup slide maybe?
If you leave 2 or 3 minutes for questions, then...
Okay, I'm very quick. I just want to talk about the current project we are working on, which is integrating SitOps in a smart factory environment. As you all know, smart factory is an important part of the Industry 4.0 movement, which it is called in Germany, I think internationally it's called advanced manufacturing. And as you know, in these environments there are highly interconnected machines and robots that work together to, for example, manufacture a project. And we want to use SitRS to integrate SitRS in smart factories. So we want to recognize error situations, materials shortage, and react automatically on them. So if a machine fails, we could, for example, call a technical decision. Yes, exactly. Okay, we want to enable a connection of production machines to SitRS, and we want to monitor smart factories using situation recognition. Okay, so that's what we are basically working on with the student project, and this is another use case for the SitRS approach. Thank you for the attention.
Thanks a lot for that nice presentation. I'm sure there are some questions for you.
Is this approach mainly, is it for monitoring, or we can also use it for reacting to the situation and really execute, critical functions?
Currently, it's just for situation recognition. There are, in this project, there are two parts. There's the situation recognition, which is done by our institute, and the reaction on the situations is done by the Institute of Professor Leymann currently. So we are only focusing on situation recognition.
Okay. Usually this kind of approach are done on a very low level, like microcontroller or microprocessors that react very quickly to such a state change. And so how realistic can this be applied? Because exposing such a thing on the internet or cloud, it's kind of, I don't know if it's as efficient as doing this on a low level and as secure as it is. Because in a critical industrial situation, I think it will face a lot of security problems.
Yes.
So how realistic can this go?
Yeah, that's a very interesting point and a very good question. Yes, you're right. It's kind of comes with efficiency and, of course, also security issues. The security aspects we haven't yet looked into it, but we will, of course, have to in these environments. So currently, in a smart factory environment of a great company, we can't use this approach without any security features. Furthermore, you talked about situation recognition based on a very low-level approach. The main goal was abstracting from low-level details. So, people who aren't IT guys can model situation templates.
It's more powerful, but I think it will face a little bit problems with efficiency, because microcontrollers usually react in microseconds. So yes. I don't know, exposing such a thing.
So of course you're right. For very, very real-time use cases, this is maybe a better approach, and I think it depends on the use case when you use SitRS. Of course, we can't compete with that.
Sure. Thank you very much.
Any further questions? Yes.
Could you go back to slide 6? Those predicates look a little maybe fixed, like a little rigid. I don't know how flexible it is, like if you want to change something.
Sorry, I didn't quite get that.
let's say if you want something more flexible, like you have this, if the memory is less than 100 megabytes, but if you have like another machine that has more available memory, and so you want to make like this predicate would be less than 200 megabytes because you have a little more available memory. So you would create another template just for that.
Yeah, you're right. However, we are currently, that's true, yes. However, we are working on an extended version of situation templates. That was some kind of first approach to situation templates. We also want to compare these nodes directly on the bottom. If the RAM of this machine is larger than 500 MBs and the RAM of the other machine is lower than 200 MBs, for example. Or if the RAM of this machine is lower than the RAM of this machine. This is currently not possible, also because of the execution approach that we use. However, when using CP engines, you can enable this, you can aggregate this on the bottom level, and of course we will also change the situation candidates. And we will also add some more powerful concepts, such as concepts of time. For example, I also want to define a situation if the CPU load is greater than 90% for over 30 seconds, because as you all know, there are a lot of peaks where you got a CPU load of 100% for just 1 second. And I maybe don't want to recognize the situations. So the concept of time will also be integrated in the future, and also the integration on a lower level.
Okay, in the course of time, I would suggest that further questions go into the coffee break, and I would like to ask our next speaker to already start setting up the machine. Our next talk is from Marigiana Skuradaki. Is that correctly pronounced? Okay, great. She's working in Leymann's group, and this takes us to business process model.